Hello students, welcome to Educate. Today we are going to continue with 6th chapter of physics of class 11th. So in previous lecture we have studied the basic concepts. Today we are going to continue from next point, so that is torque. Torque is force into perpendicular distance. If we consider the unit, so this will be Newton and meter. So unit will be Newton and meter. There is another concept, that is couple. So two equal and opposite forces, suppose they are acting, this point is fixed, so this will move in this direction, this will move in this direction, so there will be a rotation. So this is, suppose this is F, so this will form a couple. We also say it movement of force. So torque is also called moment of force. Now, next point, let's see the cross product of R cross P. If you know, this is angular momentum. If you remember the basic formula, angular momentum L is mvr and mv is p, so pr. So in case of vector, if we write, so it gives L equal to R cross P. Now we are going to check what is the result of rate of change of angular momentum. So dl upon dt, let's try to find out. So here d upon dt of R cross P, and I think you remember the basic rule of differentiation, d upon dx of function 1 into function 2 gives a db upon dx plus b times dA upon dx, right? Here the order is interchangeable. Here b I have written before and then a after, but in case of vector, keep in mind you are not allowed to change the order. If you change the order, then negative sign must be written. So here R cross dp upon dt plus dr by dt cross p. Is it okay? First function, second function differentiated, then first function differentiated, second function is written as it is, or you can differentiate first function, keep it as intact, and then after that you can do reverse. So same thing. So here R into dp upon dt, change in momentum per unit time, is force, if you remember. And here dr upon dt, distance upon time, is velocity, v cross p. And now if you remember p is mv, so just analyze it, p v cross p, that is v cross m, v cross v, m cross v. And you know v cross v means they are same vector. So theta between them, this you can write v square m into sine theta, and theta is equal to 0 degree. So you will get 0. So second term will become 0. First term dl upon dt you have got as R cross F. And if you remember, torque is tau equal to R cross F in vector form. So we can write here dl upon dt equal to torque. So this is an important relation that you should remember. Now suppose there is no torque. In that case, what will happen? In absence of torque, this dl upon dt will become 0, or L will be a constant, right? So in absence of torque, angular momentum remains conserved, and this we will make use in planetary motion also. We will study it in next chapter. Here there are two important questions. We can solve them, and we will apply the concept of equilibrium, in which translational equilibrium, it means body is not moving in straight line, and rotational equilibrium, body is not rotating. So both things we will take into consideration while solving this problem. So let's analyze the question, and then we will see how to get the result. So here question says, you were given a metal bar of 70 centimeter long. So A to B is 70, 4 kg mass, its mass is 4 kg, and you know, if this rod is uniform, in that case its weight will lie at the center of gravity. So at midpoint here center of gravity is located. You can say A to G is 35 and G to B is also 35. Then and 4 kg in mass supported on the two knife edges placed 10 cm from each end. So this is one knife edge, this is another knife edge. So this is 10 cm, this is 10 cm. Now what is left? From this point this is 25, from this point this is 25. Then there is additional condition. A 6 kg load here is suspended at 30 centimeter from one end. So you know, from here up here this is 35, so PG will be 5. So from center of gravity point P lies at 5 centimeter. There we have suspended a weight of mass 6 kg. Situation is like this. Now here there will be normal reaction, here there will also be normal reaction, and here due to weight this body will try to move in this direction. So we will see rotational equilibrium. Translational equilibrium will not be there if rod is fixed. So only rotational equilibrium will be considered. And in this direction we will take a positive torque, and in this direction if we move, we can say when we take in this direction moment of force, then we will take positive, and if we consider this direction, then we will take moment of force negative. So here, how will you take moment of force? You will take force, means suppose W1, then this multiplied by PG. The distance means this is force and this is distance. Suppose this is. So product. Similarly, here also force will be R2 and distance up to R2 you have to take. So this distance is 10 and this total is 35. So this will be 25. So you will multiply here. For this is clockwise, it means it should be taken as negative. So here what will happen? So from here to here K1G distance should be taken, and then we will multiply by this R1. So the torque, rotational torque should be balanced. So let's see the equations given here. I think you have understood clearly. So here same thing is given. When we consider this R1, so we have taken negative side, anti-clock, this is clockwise, so negative side, and then distance from this point K1G is written. If you consider W1, so its distance will be PG, which is 5, later on we will write, and then if you consider this, so R2 times its distance from here, so that will be K2G equal to 0. And values are given, like W weight is given, weight of the rod, weight suspended is given, and small g is given. So after putting these values, we will get one relation as R1 plus R2. R1 is upward, R2 is upward. So R1 plus R2 will be 98 Newton, and then after that we can put the value in second equation, and after putting values we will get R2 equal to 43.12 Newton and R1 this much. So this is how we can evaluate. Question is simple, only here we have to take into account the rotational equilibrium. Here there is another question in which also we have to consider this rotational equilibrium, and translational equilibrium can also be considered, because here this is one ladder, so it can move in this side also. So there should be a frictional force which will prevent it from motion. So we can say at this point there will be frictional force in this direction. So here there will be another force, and here there will be one force which is perpendicular to the wall, and this length is given as 3, this length is given as 1, and since ladder is mass of ladder is uniformly distributed, so we can assume that its mass lies at its midpoint. So W is shown here. This is 3 meter long. Now let's read the question. A 3 meter long ladder weighing 20 kg leans on a frictionless wall. Its feet rest on the floor 1 meter from the wall as shown in the figure. Find the reaction forces of the wall and the floor. So reaction forces are to be found. F1 you have to find out. Sorry, F1, F2 you have to find out. So as I told you, here you can take a rotational equilibrium. For this force, if you take, the perpendicular distance should be taken. So F1 times you have to write BC. If you take this force, so what is perpendicular for this? So you have to write this distance, this AE, which will be half, right? And at this point, what do you observe? Here in this direction, there will be frictional force. In this direction, here normal reaction. So resultant of normal reaction and frictional force will be F1. So this is all fact. Here Pythagoras theorem is applied to get 2 root 2, because this is 3, 3 square is 9, this is total 1. So 9 minus 1, so root 8, and then 2 root 2. Up to here, I think thing is clear. Now let's see the solution. It is simple. The same thing as I told you, every value is given. Then for translational equilibrium, so it should not move, so its weight and normal reaction should be same. So this is first equation. And horizontal forces, one force is acting in this direction and frictional force will oppose it. So that is why F minus F1 equal to 0. And for rotational equilibrium, as I told you, you will consider two forces. So one is 2 root 2, that perpendicular and force is acting like this, that is given. And then another weight is acting downward, so that is negative sign. And here the point is half. I think you remember it. If you want, I can draw the diagram again so that thing may remain clear. So here this is normal reaction, in between there is F1, and here this is wall, this is 2 root 2, and here there is one force. If it is F1, then this will be F2. So here let's write it F1, this is F2, and here there will be force of friction, and here weight will act downward. So let's evaluate it. So for rotational equilibrium, we can write this relation. W will be total weight is given. So just make it half, and G, you know, 9.8 Newton. Here 9.8 Newton, no, this is 9.8 times normal reaction is given, that is this much. And then you can get value of N. I think there is slight confusion here because of this. So weight is given as 20 G. So 20 G, G means here there should be multiplication sign. So let's write here 20 into 9.8 Newton. So that will be 196 Newton. So N and W both are equal from here. So you can get that value. Then we can evaluate F1. So F1 will be W upon 4 root 3. And then you can evaluate it. Similarly, F and F1 will be same. And then after that, as I told you, that here F2 will be found by using Pythagoras theorem. Friction force is like this, perpendicular like this. Then you can evaluate, and finally, if you want to find out angle that it makes, then normal reaction and friction force, you can calculate angle. So that will be around 80 degrees. So just you have to understand the question. I don't think that there will be difficulty in evaluation. Only rotational equilibrium you have to consider. So one here, this normal reaction weight should be equal, and here force, the two forces, one is frictional force, another is F1, must be equal, so that the body Friction force will act in this direction and this force will act in this direction. So body should not move means this ladder should not move. So that situation we have to consider. So I don't think that you will have any problem. Now let's consider the concept of moment of inertia. So what is moment of inertia? What is its role? So moment of inertia is very important concept in which we generally write its notation. We write I times mass into distance square, say mr square. We write this relation. If we consider its unit, so this will be kg meter square. So it is simple. Now suppose this is axis of rotation and there are many masses. Say m1 mass lies here, m2 mass lies here, and say m3 mass lies here, and its distance from axis of rotation, say this is r1, this is r3, this is r2. In that case, moment of inertia will be sum of all moments like m1 r1 square plus m2 r2 square plus m3 r3 square, like this. So you can evaluate. Now, if there is body like this, suppose body is like this, and this is axis of rotation, and there are different masses, say at distance r1, another mass is at distance r2, at third mass is at distance r3, then r4, and there are n masses. So here one more concept we can use, I equal to mk square, where k is radius of gyration. So how to find k square? So for finding k square, we find r1 square, r2 square, r3 square, and so on till rn square, and then divide it by n, and we can easily get. So that is also one way. So you can evaluate radius of gyration and then you can get moment of inertia. Now, if we consider the role of moment of inertia, so moment of inertia in rotational motion is equivalent to force in linear motion. Like here, if we write some relation, suppose we write F equal to ma. This is linear motion. And if we consider rotational motion here, so here it will be force will correspond to torque equal to moment, this mass will correspond to moment of inertia, and A will correspond to alpha. Any other relation, suppose we write P equal to mv. So in rotational motion, P corresponds to angular momentum and mass will correspond to this moment of inertia, and velocity will correspond to angular velocity. So it will play the same role as mass plays in case of linear motion. So its importance you have understood. Similarly, suppose you write kinetic energy here, you write 1 by 2 mv square. So in case of rotational motion, we can write rotational kinetic energy. So that will be I into 1 by 2 into I, and V will be replaced by omega square. So any relation can be written and they all will be similar. Later on we will see the derivations, also different type of derivations. So here moment of inertia of a rod is given. So suppose this is rod and this is axis of rotation. At this point, say total mass is m by 2 in this side and m by 2 is in this side, and this distance is say r by 2, this distance is r by 2. So moment of inertia, if you evaluate, so 1 by 2, not 1 by 2, mr square only. So for first m by 2 into r by 2 square, this square plus same, you can repeat it, m by 2 and r by 2 square, and then you can simplify, same thing is written here. Now further, here certain examples are given of, suppose practical examples for this moment of inertia. So here you will find there is one device called flywheel. It is very important thing. The property of this extremely important quantity I as a measure of rotational inertia of the body has been put to great practical use. The machines such as steam engine and the automobile engine, etc., that produce a rotational motion have a disc with a large moment of inertia called flywheel. Because of its large moment of inertia, the flywheel resists the sudden increase or decrease of the speed of the vehicle. It allows a gradual change in the speed and prevents jerky motion, thereby ensuring a smooth ride for the passengers on the vehicle. So you have understood the importance of flywheel. Now we are going to see the moment of inertia of different bodies. Here, derivation of these expressions are not in your syllabus, so only few things you have to study. But it is advised that you should memorize that what is inertia of these bodies, because in exam they will be asked like here. One thing is also important: what is axis of rotation? In this case, axis of rotation like this. Here axis of rotation is like this. Here axis of rotation given. Here also, here. So axis of rotation is also one important aspect. So moment of inertia of like here thin circular ring is mr square. Thin circular ring about its diameter. Keep in mind, this is perpendicular to the moment here. This you have to see the axis of rotation. Here, axis of rotation is like this. In that case, moment of inertia is changed of the same object. Now here, moment of inertia about perpendicular ml square upon 12. Then here, this is a disk, so perpendicular to the surface, that is mr square by 2. Here, if you are taking a long diameter, in that case, it will become mr square by 4. If you are considering hollow cylinder and about its axis, you are taking its moment of inertia, so that will be mr square. And if you are taking solid cylinder, in that case it will be mr square by 2. And if you are considering suppose sphere, then its moment of inertia will be 2 mr square by 5. So up to here, I think you have understood. And in next lecture, we will see its dynamics, means different type of relations we will try to derive by using calculus and some basic methods. Thank you for watching. Team Educate